Okay, good afternoon, everybody. My name is Shankar Shastri. It's my great pleasure to welcome you to this edition of the C3.ai Digital Transformation Institute Colloquium. The mission of our institute is to have a coalition of the leading scientists from around the world to have a coordinated effort to develop both the science and technology of what is meant by digital transformation, which is really the confluence of AI, machine learning, data from IoT sensors, and in fact, modern data analytics to be able to think about new products and services affecting every aspect of our life. Berkeley and Illinois are the co-lead institutions on it, and the partners include CMU, KTH Stockholm, MIT, Princeton, Stanford, and the University of Chicago, as well as the Berkeley National Labs and the National Center for Superconducting and Its Applications, NCSA. That's at Illinois. The industrial sponsors, primarily C3.ai and Microsoft, but there's also support from AstraZeneca, Baker Hughes, and Shell. Of course, you know, there are some of the main things we do in the institute is have calls for proposals, and when there are proposals, there are perhaps as many as 30 other university partners also involved in the research of the institute. I encourage you to take a look at our website to see all of the exciting programs. The coming events in this colloquium are certainly next week, October 14th, Universal Laws and Architectures. And John Doyle, a colleague at Caltech, you know, he's been saying for a long time that highly optimized systems actually are brittle. And he'll talk about this, his take on the instantiation of that on October 14th. Sanjay Chakratai, I think that's Texas A&M, is going to talk about going from 5G to 6G and how machine learning will play a really important part of that transformation. Actually, we had a workshop last week with Muriel Medard and a colleague at MIT, which already began to cover some of this ground. You know, the workshops are repositoried on the YouTube channel. I encourage you to take a look. Wei Liu will talk about the built environment, and Kai Yuan will talk about the second set of proposals. I think University of Illinois about you know, how do you tell farmers how much carbon credit they get for their different actions? And if you expect them to contribute, you've got to tell them how they get credit. That's that. The next workshop, the workshops are longer, in-depth series. October 26th and 28th, our fellow chief scientist with Tandy Warno, who's on this call from Illinois, Kostas Panos, who is the organizer of a workshop on the digital transformation of the built environment. And I really recommend that, because in this, after you come out of this, you'll realize that modern buildings are really more about the operating system of the building rather than about you know, all the concrete and glass that you see. All the activities of the institute, a lot of the activities of the institute are on the YouTube channel. That's the YouTube, you know, C3 Digital Transformation Institute. So coming to the format of today's colloquium, it's a roughly 40-minute presentation and some Q&A. You can use the Q&A feature to ask questions, upvote questions. We'll try to answer them as many as we can. I'll certainly keep an eye on them. Larry Larbaugh, who's on it, will also monitor them. So it's a great pleasure to introduce today's speaker. We'll talk about hierarchical control of cyber-physical systems with applications to traffic management. It's my dear colleague, professor of ECS at Berkeley. He got his PhD at the University of California, Santa Barbara in 2000, received the NSF Career Award, the Ekman Award. It's really a young control theorist, below the age of 35, I think. In 2006, and then he got the Roberti Prize, named after the famous Italian researcher. That's for the age of 45, maybe younger. and then the Siam Prize. All pretty prestigious awards. He's a fellow of the IEEE. And without further ado, let me present Murat. And Murat, I will mute myself. I'll come back at the end of the call. So thank you very much for doing this.
Thank you, Shankar, for the introduction and the invitation as well. Really happy to speak here. So many people I know in the audience. So I will share screen and go to the slides. I assume everybody can see that, right?
Yes, that's great.
Cool. Okay, so you already heard the title, just to get into it right away. Okay, that's not good. Okay, so we'll be talking about large systems that integrate many components, and at the same time, they must satisfy complex requirements. That's the challenge we're addressing in this talk. And I'm a control theorist, and the design verification methods we have available are typically limited in their scalability to the scale of problems that we're talking about here. And also the types of requirements that control theory has traditionally addressed does not extend to the complex requirements that I'm interested in. So this talk will be about how we manage this complexity, and hierarchical approaches will play a key role. And of course, we know from many types of networks that hierarchical organization is the key to managing complexity. And we'll see some projections of these ideas to control. In particular, a running example in this talk will be vehicle traffic management. So what you see at the bottom here is a figure that was associated with a NSF CPS project that recently ended, that we named a traffic operating system. And it shows the hierarchies involved in managing traffic flow, starting with vehicle level control at the very bottom, and road link level control, which includes things like signal timing and so on, in the middle. And at the top, network level control, which involves routing and related problems. And in this project, we explored cross-layer problems, how one layer can inform the other and so on. So this will be one of the running examples. So the talk is organized into two parts. In the first part, I'll talk about hierarchical control. And the key concept will be the concept of an abstraction. And we'll talk about applications to vehicle level control and signaling at intersections, which basically cover the lower two layers of the diagram that you saw before. In the second part, I will talk about population games, which are relevant to routing games. And in particular, we'll talk about convergence to Nash equilibria in these classes of games. And that has to do with the network level in the previous diagram, because routing belongs to that level. And I will do an illustration based on a mixed autonomy traffic flow problem. And we'll see how the Nash equilibria concepts and convergence to Nash equilibria in evolutionary dynamics can be argued. So going back to hierarchical control, this is part one. So we all know hierarchical architectures are critical, and any complex system pretty much you can imagine is organized into a hierarchy. If you think about autonomous operations like an autonomous vehicle control, you'll at the very top have high-level decision-making capabilities. And then below that, you'll have planning, guidance, perhaps supervisory control, depending on what the application is. And those typically generate trajectories or set points for a low-level feedback control algorithm to follow. And of course, the feedback control interfaces with the physical system. So the question is, how do we make formal guarantees for a control stack like this? So there are different layers here, and associated with each layer is typically separate semantics and separate sets of tools models. So different multi-world views, so to speak, as was articulated in this paper at the bottom by Praveen Baraya. So the question is, how do we connect these worlds and reason about the whole system? So I'm a big fan of Norse myths. So this multi-world view of hierarchical systems reminds me of the tree Yggdrasil that connects different worlds in Norse mythology. Asgard is where the gods live, Midgard is where humans live. There are bridges between them and so on and so forth. So it's a comparison that I will be following. So in the next slide, the role played by Yggdrasil will be the notion of an abstraction. So I'll start with discrete abstractions. So what we have here at the bottom is a continuous state model that we are trying to control. And perhaps we are trying to design a supervisory control algorithm. And possibly, and very often, to satisfy some complex requirement, perhaps expressed in temporal logic. To be able to design a controller for that, it's most reasonable to reason at the top level, where we have a finite state abstraction. A finite state model is more conducive to reasoning in terms of temporal logic. So the question is, how do we stitch this with the actual continuous state model? How do we extract an abstract finite state model from a continuous state model? And once you have the control designed for the finite state abstraction, how do you refine it back to the continuous state model? So how this is done is typically as follows. You take your continuous state space at the bottom and partition it into cells. These could be hyperrectangles, for example, and you treat each one of those as a discrete state. And now you perform reachability analysis to find, starting in one discrete state, that is one box of initial conditions, where you land under the action of one control, okay? And the other discrete states, the other boxes that you can transition to, basically become the successors in the finite state model. So this yields a finite state model that is amenable to formal methods, formal synthesis, with which we can address complex requirements given in temporal logic. So the formal guarantees you obtain with the discrete model also carry over to the continuous model using appropriate simulation relations. There are many of them. In our work, we typically use the notion of alternating simulations. And probably the most up-to-date work on simulation relations and the hierarchies of those is one by Reisig et al. That received the Axel B award recently. So this is a stylized illustration of a discrete abstraction. So we have only 4 boxes here. The space is split into 4 cells. And so the green set is the reachable set from the gray box. And because it overlaps with the yellow and purple boxes in the discrete abstraction, we direct transitions, assuming this reachable set was obtained with under control U1, we direct transitions from the purple state to the yellow and, gray state to the yellow and purple states. And let's say under control U2, you have transitions possible to the red and purple states. So if your goal in synthesis was to say avoid unsafe behavior, which might be associated with the red state, then the goal would be to eliminate control U2. That's a very overly simplified illustration of how the reasoning works in abstraction and synthesis. So some history of these approaches in control synthesis, hierarchical control. So partition-based hierarchical control ideas started appearing in the 1990s. Some papers by Lunze, Peter Keynes and co-authors Reich and Yang. And in the past 2 decades, there has been a lot of work, and this is by no means a complete list, but some names that come to my mind who worked on abstractions and symbolic control, some of which I'm sure you recognize. So many advances have been made. However, there are computational bottlenecks that still severely limit the applicability of this approach. And there are many of them. First of all, obtaining an abstraction requires reachability analysis, forward reachability analysis, which is known to be a computationally hard problem. And even if you could somehow overcome this problem, then you deal with, as the number of continuous state variables increases, you deal with an exponential growth in the number of discrete states, as well as growth in the number of transitions between those states. And that leads to a lot of difficulties for synthesis, as well as memory requirements in even storing the abstraction. So we've been doing some work over the past 6-7 years, probably, trying to overcome some of these bottlenecks. So in this slide, I talk about some of our work on trying to make forward reachability analysis faster and more scalable. And I organized those under 3 bullets, 3 types of methods that we've been developing, and they are summarized in this book that was recently published, which focuses primarily on interval reachability analysis, meaning that we're interested in bounding the reachable set with hyperrectangles or multidimensional intervals. So although some of these methods are not limited to this type of set representation, this book focused on that in particular. The reason was that the abstractions and discrete state representations are consistent with intervals. That's the only reason. So one set of tools comes from contraction theory, which allows us to judge whether solutions starting in the vicinity of an initial condition lead to trajectories that converge to that trajectory or diverge from it. In any event, we get some growth bounds around sample trajectories. And that's one way to rapidly get outer approximations for reachable sets. And this is illustrated at the bottom left. And now we've been using a lot of ideas from monotone systems theory. Monotone systems are those that preserve a partial order along system trajectories. So this allows us to sandwich the reachable set between 2 sample trajectories. Monotone systems by themselves are a rather narrow class, but we've been using various types of extensions, including a notion of mixed monotonicity that significantly broadens the class of systems to which we can apply these tools. And the result is a set of reachability tools which are extremely scalable and fast. And more recently, we've been starting to look into statistical learning approaches where we basically sample trajectories. This is a data-driven approach. It doesn't rely particularly on the type of system model we're dealing with. The main requirement is the ability to evaluate system trajectories, perhaps through a high fidelity simulation. And what we get out of this is probabilistic guarantees, as well as sample complexity bounds. So if you want a certain level of accuracy and you want a certain level of confidence, these sample complexity bounds spit out the number of samples you should be taking. So in the statistical learning jargon, this is basically the problem of generalization from sample trajectories. So some of these statistical learning results made it into this book, but we've been doing a lot more work and expanding our results in this direction in the last year or so. So we achieve further scalability by using parallelization in the computations, especially when we rely on sample trajectories. Parallelization is greatly helpful. So we reported some results in CAV 2020. So what you're seeing at the bottom, and let me first be clear that this is these plots are for examples to which the methods that I mentioned are applicable, and the plots go by the order. So the one on the left is for contraction, the one in the middle is for monotonicity, and the one on the right is for sampling approaches, statistical approaches. So they are showing results with the speed ups that we gain with parallelization and how many state variables in a model we can achieve. This particular example is for a traffic flow model, which has a sparsity structure. And the parallelization meshes really well with sparsity structures in the dynamical system model. So as long as you have enough sparsity in your model, these methods can also take advantage of parallelization. So what you can see here is results with how long it takes to do the reachability analysis with several AWS platforms with parallelization. The black line is the baseline. It has no parallelization. And you can see that it basically, once we reach about 1,000 states or so, that starts taking hours. But with parallelization, we can go up to, in an extreme case, up to billions of state variables. The example we use is an easily extensible line graph of road segments. So that's how we expand the model while preserving the sparsity. So this much was about forward reachability analysis, but for synthesis and so on, we still need an abstraction. So in obtaining the abstractions, you have to make many separate reachability analysis. For each cell, you need to know which other cells you can transition to. So here too, we took advantage of sparsity structure in the dynamical models. And what we do is we actually do the reachability analysis for separate dimensions. And that's how we are able to take advantage of sparsity. And that leads to a drastic reduction in the number of reachability computations one has to do to obtain an abstraction. We do further tricks. We use, so this was for obtaining an abstraction or reducing the number of reachability computations to obtain an abstraction. For storing an abstraction, we can also use sparsity tricks. This has less to do with sparsity in the dynamical model, but more about using only a few transitions to represent all others. For example, if our system has monotonicity properties, knowing the transition from one state to the largest state in the partial order will allow us to bound all other transitions with that largest state. So we take advantage of these partial orders to be able to obtain more sparse abstractions that we can store easily. We have done other work such as lazy control synthesis, as well as compositional synthesis with assumed guarantee contracts, and 2 representative papers are cited at the bottom. So the monotonicity properties that are mentioned in the last bullet are actually naturally satisfied in a number of driving scenarios. And in this last paper by Smith, Saud, and myself, we gave 2 examples of vehicle following as well as a left turn scenario where we can take advantage of monotonicity. So another example of using abstractions for synthesis and then refinements is for reactive signal control for traffic flow. So one of the first applications where we actually observed these monotonicity properties and their usefulness was these traffic flow models. The so-called self-transmission model has some inherent monotonicity properties which made reachability analysis really fast. And then we looked at some network structures where you lose monotonicity, but you still retain a notion of monotonicity that we call mixed monotonicity. So this application basically was the genesis of some of the concepts that we were able to introduce and generalize. So the goal in signal control is, for our purposes, to meet some finite horizon goals expressed in temporal logic, such as dissipating queues, avoiding saturation, and so on. So the classical approaches to reactive signal control are based on steady state assumptions. The commercially available software Synchro, for example, works that way. It assumes steady state conditions. And whereas here we're trying to address a more dynamic environment. So what we do is we take a continuous flow model, such as the self-transmission model. We do a finite abstraction and then do synthesis so we can satisfy a temporal logic requirement such as dissipating queues and so on. And then that becomes basically the signal control policy. This actually is rather intuitive as well, because when we take our state space, each state dimension is the density on a road link, right? So each of the cells, when we do the partition, is basically telling us roughly what kind of traffic conditions we have. Like link 1 has high density, link 2 has low density, therefore take this action type of control. So the resulting control policies are actually very easy to interpret. So we summarize this approach in this Control Systems magazine IEEE article, which is a tutorial, and we also explain some of the underlying methodologies in this paper. So besides discrete abstractions, there's also the notion of a continuous abstraction, where you take a continuous state dynamical model and abstract it into a lower order, potentially simpler looking dynamical model, but lower fidelity. You could be using such a model as a stepping stone, for example, to do discrete abstractions, because the computation to get from a continuous to a discrete model is very heavy. you might be wanting to start with a lower order model. So this might be an intermediate step. Or you could be using this lower fidelity model, in and of itself. So you might be using it for motion planning, for example, or if you're dealing with a large network, you may be trying to aggregate the nodes of the network, so you can do a high-level control and then break it down to the individual nodes. So the refinement in this case takes the form of basically a tracking controller that treats the abstract model as a reference model, similar to what we know from model reference control, for example. So, and the way we establish a simulation relation between those two, the abstract and the concrete models, is through a dissipation inequality, whose aim is to establish the closeness of the outputs of the abstract and concrete models, which is denoted by y and y hat, and t is the time argument. So v here is a Lyapunov-like function that needs to satisfy the inequality that you see, the two inequalities at the bottom. The last inequality in particular tells us that when v is 0, the two outputs of the systems are identical. Okay, and the first inequality gives us a convergence property to 0 in the ideal case. But what we do here, and that's very important, is we allow this residual term to remain, which then leads to a small error in the tracking of the output by the concrete model. The reason we need this residual term is as follows. So without it, everything would be perfect because the output would converge to the output of the abstract model. The problem with that is when this residual term is not there, this boils down to a model matching problem from control theory, which relies on very heavy, very restrictive geometric conditions. Okay, and to be able to break them and make this more applicable, this residual term is extremely useful. So since this function v is establishing a simulation relation, Girard and Papas in their 2009 paper called it a simulation function. So what we did here was to allow this residual term to depend on the states of the reference model, which led to a major simplification or relaxation of the geometric conditions that are required. So in the next slide, I show you one example of where these continuous abstractions might be used. For example, you might have an autonomous vehicle, and you might be trying to do planning and control. So for planning, say you want to do model predictive control, because it's easy, optimization based, you can do it in real time. But for model predictive control, you may be preferring a lower order model and perhaps a linear model, which is even better. So the abstraction can serve that purpose. And then the refinement, which is basically tracking, would then give us a low-level controller that makes sure that the actual plant model follows the trajectories generated by the planning model. So with this separation, the heavier computations for finding a simulation function and the tracking control will be pushed offline, and the real-time computations will be performed on the abstract model, which is simpler. So you can use this for MPC, or as you see in this paper that I cite at the bottom, you can also use it as a stepping stone to obtain a discrete abstraction. That's what we did here. This was for a ship control model that included a dynamical model. So what we did was to use the continuous abstraction first to obtain a kinematic model. And then the kinematic model is nonlinear. And then we do a discrete abstraction on that reduced order kinematic model. So this work was motivated by, in fact, ship docking. A lot of the docking operations, I was told, are done still manually, despite other advances where people are doing everything else autonomously. And so what you're seeing on the picture on the right is basically the transition state to docking, where you're in the harbor area and you're trying to follow a reach avoid specification. So this is me on a ship simulator at this facility of Rolls-Royce Marine in Norway. Since then, they've been acquired by Kongsberg Maritime, but they are still there. So now in this formulation that I gave you, so we have this residual term, and therefore the tracking error depends on the states of the abstraction or the planning model. So our goal is to keep the tracking error small, because what we have to do eventually is we have to bloat the obstacles by the amount of tracking error, and we have to shrink the target set, as you can see in the figure on the right. We have to shrink the target set by that amount. So ideally, of course, you want to keep the error small. But how do I keep the error small? The error, if I go back, will depend on the residual term. And the way to keep the error small would be to make the inputs to the abstract model small and keep the states of the abstract model small, right? But that really leads to restriction on the planning model. So the permissiveness, so to speak, of the planning model will be diminished. So this leads to a trade-off in tuning the planning and the tracking models. And so in a separate paper, we showed an optimization procedure can help us in finding the right spot while making the planner more permissive. We can actually also keep the tracking error small. Another application of continuous abstractions is to network aggregation. So your dynamical model may be a large-scale network of interacting agents. And the abstract model may be an aggregation which combines some of the nodes into aggregate nodes. Things like that were done earlier in the power systems literature, relying on things like time scale separations, which are induced by weak connections between areas and so on. With the tools that I described, we actually don't need any of these weak coupling requirements. So in this paper on the left, we gave an example with building temperature regulation, where we aggregate different rooms treated as nodes in the dynamical model into wings of the building, and we obtain a smaller order model that way. And I've been using a lot of these aggregation concepts in synthetic biology, particularly in multicellular systems, in trying to obtain gene expression patterns. And so some of these reduction ideas have been extremely helpful. So before I move on to the second part, I want to do this intermezzo, going back to this diagram from this project. So part of this project had a transition to practice component where we demonstrated vehicle platoons in urban traffic. The goal being to increase the capacity of intersections with this. Platoons had been demonstrated, of course, many of us know, earlier on freeways. So what is new here is doing this in an urban traffic environment. So the way to increase the intersection capacity, which is one of the biggest bottlenecks, is to move them as a platoon. So typically you have this slinky effect. When you're at the red light and it turns green, one vehicle will start moving, others will follow, but the gap between them will increase. But if you can move them with a constant headway as they accelerate, and that was the control challenge in this demonstration, then you can easily double or triple in some cases the capacity of the intersection. So that's exactly what's happening here. This was in Arcadia, California, close to Pasadena. So these three vehicles, the blue followed by the two white ones, are the platooning vehicles. There are drivers, basically me and 5 students who joined this demonstration in those vehicles, and we are keeping 6 meters between the vehicles. We steer, but we don't touch the gas pedal or the brake pedal. That part, the longitudinal control, is done automatically with vehicle-to-vehicle communication and vehicle-to-infrastructure communication as well. So the reason these experiments were done in this venue is because there were 8 consecutive intersections that were instrumented to send signal phase and timing messages to the vehicles. This had been done for a different project. We just piggybacked on that. So that way, we don't have to do anything when we're at the light. So that basically is a summary of this demonstration. So with that, I'll move to part 2. And with part 2, we'll be moving to the network level control and start looking into routing problems. And we'll be talking about population games, a certain thread of game theory. for the network level. So what are population games? Population games deal with large numbers of agents. So, and that's the situation where the traditional approach of keeping track of players one by one is no longer tractable. Instead, population games will keep track of the proportions of agents, proportions of the whole population using each strategy. And the assumption is that there will be a finite number of strategies. So one of the examples of this, so it's at the end of this, you get a continuum model, which makes it easier to reason about. So one standard example of a population game is a congestion game. In this picture, you see one origin destination pair and 3 routes that join the origin to the destination. So in these games, each route becomes a strategy for the users to choose from. And then you assume a constant demand that would be the total flow wishing to flow from the origin to the destination. The question is, how will that split itself into these 3 routes, right, in this example? So that gives you a state space that is a simplex, because the sum of the flows will be constant, and the flows will, of course, be non-negative. The question is, what is an equilibrium, and how do the how do the trajectories, if the drivers have revision opportunities, where does that converge to? So population games has a rather circuitous history. So this book that you see on the right by Beckman and co-authors, some people call it the BMW book, is from 1956. And it was preceded by the famous paper of Wardrobe. So both papers study equilibrium concepts in route choices. Okay, and they do this pretty much independently of any kind of reference to games. It was others later who made the connection to the work of Nash, which also came in the 1950s. So later on in the 1980s, there were studies by evolutionary biologists, among them John Maynard Smith, wanting to take Nash equilibrium concepts and adapt them to evolution. And they led to some evolutionary dynamical models and some refinements of Nash equilibrium concepts, such as the evolutionary stable strategies and so on. So it is really now the confluence of all these different separate threads that we call population games. And population games include dynamics in the form of strategy revisions, which is a much broader interpretation of what you would think of as evolutionary dynamics in the biological context. So the example we saw here with the congestion game is has only one population. So in general, we can allow multiple populations. So the state space, the social state vector, will live in a Cartesian product of simplices. So what defines a population is basically agents that have the same set of strategies and the same traits. So they can be treated as anonymous and lumped into one population. So the moment there are discrepancies, you have to split them off into different populations. The key to the definition of a game, of course, is the payoff. Payoff is a map from the social state space to Rn, which is a vector of the payoffs. So going back to the congestion game example, the way we get a payoff, first of all, you don't really have payoff when you're in traffic, you only lose time. So the negation of the total travel time is interpreted as a payoff. So it's negative of the delay that you encounter. And the structure of S is as shown at the bottom. So first you have a routing matrix. X is a vector of route flows. R is a matrix that has only ones and zeros in it, showing which link lies on which route. So when you multiply R and X, you get a vector of flows per link. And for each link, you have a delay function. The more flow you have on a road segment, the longer it will take to go through it. So that's what the non-decreasing delay functions do. And then the sum of the delays that you encounter on your route is the total delay. And that's accomplished by multiplying with R transpose. So that's why F has this structure with R transpose on the left and R on the right. So the Nash equilibrium definition is similar to the finite player case. So first, you have the notion of a best response. So if I give you a constant vector of payoffs, I tell you these are the payoffs that you get by choosing any strategy, then the notion of best response is the state, the social state that maximizes the inner product of X with the payoff vector. Naturally, if the payoff vector has one entry that beats out all others, that's the most attractive strategy. So the optimizer in this case will be one that lies in the corresponding vertex of the simplex. So a state is called a Nash equilibrium if it's the best response to the payoff at that state. So basically what we did here is we replaced that constant vector pi with f of x bar, okay? A point x bar satisfying this inequality is a Nash equilibrium because there is no incentive for a fraction of agents to switch from what they were doing if you're at that state. So evolutionary dynamics accounts for players revising their strategies when they have the opportunity to do so. And integral to the notion of evolutionary dynamics is the notion of a protocol, which basically describes how agents revise their strategies when they have the opportunity. For example, there's a so-called Smith protocol, in which the probability of switching from strategy I to strategy J is proportional to the payoff that strategy J offers in excess of the strategy I's payoff. So the actual model is stochastic because there's an assumption that the revision opportunities are Poisson distributed in time. And then you switch from one to the other with a probability that is dictated by the protocol. But typically what's done is you will look at differential equation approximations of those that are typically accurate on over finite time horizons when the number of agents goes to infinity. So this is a typical evolutionary dynamics model that you see at the bottom. The first term is telling you the rate at which users are switching from J to I, and it's summing over all other strategies switching to I. So that has a positive sign. It's showing accounting for the increase in the users following strategy I. The negative term is the outflux, those users in strategy I switching to other strategies that they find more attractive. So for each population, the populations are indexed with R, we have a separate evolutionary dynamics model that I denote as EDM. And at the end of the day, what we have is separate dynamical models that are coupled through the payoff, because that pi in the model was really the payoff vector f of x. So, and there we go, we have a feedback loop. It's every control theorist dream. You look at a problem and it presents itself as a feedback problem. So in this case, the problem is to establish convergence to Nash equilibria through these evolutionary dynamics. It is not something that you can take for granted. There are many examples of non-convergence, periodic orbits, limit cycles, even chaotic dynamics that are beautifully described in this beautiful book by late Bill Sandholm. So establishing convergence is critical because it serves multiple purposes. First, a lot of the studies in the literature directly look at this static problem, right? They look at Nash equilibrium and is this an efficient equilibrium? What is the price of anarchy? They address questions of this form. But if you're not converging to the Nash equilibrium in the first place, what good are these studies, right? So establishing convergence actually establishes the operational significance of the equilibrium and justifies many studies on equilibrium. In addition, very often these protocols are myopic. They don't require global information. You sometimes just look at your neighbor, what they are doing. If they are better off, you start doing what they are doing, right? So these silly local rules can actually lead to convergence to Nash equilibrium, which actually is even a stronger result. It also addresses some of the criticism of Nash equilibrium because it doesn't now any longer require too much information. So there are many results in the literature. I will just talk about one thread of results. And that's the case where the map F, which defines the payoff, is a monotone map. And the definition is as in this inequality. So the paper by Hofbauer and Sandholm in 2009 established a complementary condition for the evolutionary dynamics model for this feedback loop at the top, so that you can guarantee convergence to Nash equilibria. So our colleague Jeff Shama, who is now at UIUC, in this paper in 2013, interpreted the complementary condition in Hofbauer and Sandholm as a delta passivity property, passivity being a standard control theoretic concept. So in a recent result with my friend and collaborator, Nuno Martins, we generalized this notion further. Now we don't really need the monotonicity property of the payoff. We need a more relaxed version, which is what you see at the bottom, essentially an incremental quadratic constraint on the payoff map F, which in the special case where the matrix M in the middle has the form at the bottom, collapses to the standard monotonicity notion. Okay, so it's a more general notion of monotonicity for the payoff. Oops, did I skip a slide? No, okay. And here's why we care about this. So this is a congestion game with mixed autonomy. And this is one of the reasons why I showed you that Intermezzo. You saw our vehicles, the autonomous vehicles, keeping a short headway, whereas the other vehicles were separated much farther apart, right? So that means you have two classes of vehicles in this setup, one of which uses the capacity much more efficiently than the other, the autonomous ones do, right? Because they keep a shorter headway. The regular vehicles, on the other hand, don't use it, use it less sparingly. But at the end of the day, both groups are subject to the same delay if they are using the same road, right? So because the traits are now different, you have to separate those into two populations, autonomous versus regular. So we follow this model that's due to our colleague Roberto Horowitz and Negar Meir, who is now at UIUC, of mixed autonomy. The payoff map in this case is adjusted as you see at the bottom. So you basically discount the externality of the autonomous vehicles by a number mu that is smaller than 1, because those are more thrifty in using the resources, right? So you look at the autonomous flow, regular flow, you discount the autonomous flow with mu, and you generate an effective flow, and you apply the delay functions to that. But then you generate the total delays the same way, whether it's autonomous or regular. So now the structure F has changed because of that mu, and when it's 1, you recover what we had before. So with that, if you reevaluate the monotonicity of the payoff map, it disappears. You no longer have monotonicity in the strict sense. But with a weighting factor you put in the middle, this matrix M, where the W in it includes this factor mu, you have the generalized notion that we had in our paper. So this payoff is not monotone unless mu is 1, but we have the more general notion. And the complementary dissipation property can be shown to hold for various classes of revision protocols. So the same kind of convergence guarantees that you would normally obtain for congestion games follows in the mixed autonomy case as well. We also studied an extension to the case where the payoff is not just a static map F, but rather a dynamical process itself. So to conclude, we talked about hierarchical architectures, and they are critical to cyber physical systems, in fact, to the organization of any complex system, and how abstractions helped us to obtain formal guarantees for the whole stack. So as you've seen in the traffic applications, there are research opportunities for reasoning across layers and for interconnecting as well the layers going forward. So here's some new work that we are doing that we started relatively recently. So we're looking into transportation management under extreme demand conditions, and a motivating application is something that unfortunately we have to live with nowadays in California, frequent evacuation scenarios. So what you see at the bottom left is a picture from the recent evacuation of South Lake Tahoe. Invariably, these lead to traffic jams, making you question whether it was worthwhile evacuating in the first place. So I've been told that there are more than 100 zip codes in California where the exit capacity of the town per resident is lower than what it was in Paradise when the fire broke 3 years ago. And 85 people died in that fire. Some of them were trapped in their cars. So how do you make evacuations more efficient? So we are collaborating with this company, Zone Haven, which provides a collaboration platform between first responders and the public. And they have a public-facing app and a first responder-facing app as well. So what they've done is they basically split the cities into different zones. And for each zone, they have household data and other relevant data. So what can we do? So our goal in this project is to provide decision support to first responders. And we've talked to various fire chiefs and police chiefs in trying to formulate our problems. So, and one of the big issues is how do you what are the control knobs if you want to make evacuations more effective and avoid traffic jams to the extent possible? There are some. For example, you can, first of all, sequence the evacuations by zone. You can find the sequence that's best for the evacuation as well as the timing. In addition, you can do things like road closures, or you can reallocate lanes. If you look at the picture at the bottom, there are 2 lanes that are not being used because it's going in the opposite direction. So it's often possible to redirect them as long as you allocate some lanes for emergency vehicles. In addition, we've been told that there are sometimes refuge areas, such as large parking lots, that are relatively safe from fire. And in case of huge traffic jams, you can actually redirect a proportion of the traffic into such areas. So this is ongoing work. And with that, I will conclude. And a few representative papers, not exhaustive, but some that may be broadly appealing. And I would also like to acknowledge support from National Science Foundation and Air Force in the form of multiple grants that covered the results that I discussed. And I also would like to thank all of my collaborators for their contributions.
Wonderful. Nice talk, Murat. Thank you very much. Hey, there's a wonderful trade-off there between, so much of routing is based on sort of static models, and the idea that the decisions actually influence the routing is a good one. I know that there are several people who are working on this who are in your audience, and I wonder if they're going to jump in and ask questions. The one that Babak Kafarzadeh wants to know is, does mixed autonomy mean that vehicles have different time value, different payoff? That's the first question.
I didn't quite get the questions. Can you repeat?
Yeah, I think by mixed autonomy, that was where you had the players who were, autonomous and non-autonomous. I think that was it.
Yeah, autonomous. And normally what you do is you generate populations by origin-destination pairs. But in this case, you also split each origin-destination pair into vehicles that are autonomous versus those that are human-driven.
Let's see. I have some problems with my Zoom here. Larry, can you just sort of monitor those questions as I try to get my Zoom back to snuff? I don't know what happened to it.
Sure. I'm not seeing any other questions in the Q&A. If somebody has a question.
Let's see. Let's ask Chinmay if he's on the call here. Or Chinmay, Shazej, any of those folks here? Or...
So there is a question for Chinmay. I don't know if you can see this, Murat, but I'll read this.
Yeah, I see it.
Okay. Can you elaborate on your last comment about the case when the payoff matrix is dynamical process, and what sort of results you have seen in that area?
Oh, okay. So actually we built on some results that Jeff Shama had done. So the case where the dynamical process is the replacement for static payoff is, imagine having a little bit of lag in the information you're getting. So if you're using Google Maps, right? It shows you the payoffs basically. It shows you several routes that are almost the same duration. But then that information may already be a little bit obsolete by the time you look at it. So there could be lag dynamics associated. You could just take that map F, apply it to a lag filter, and the output of that could be construed as what you're receiving. So it could be as simple as that. But there could also be other, physical dynamics involved before things settle into a steady state payoff, right? You can have Q dynamics, other things. There are many things you can actually model dynamically. I'm not sure if that answers the question.
Murat, let me jump in also to a question there. The network that you chose for that mixed-autonomy was this same network that they use for the so-called Bray's paradox.
That's right.
And so the question is, as you extend this to more complex networks, what's your sense of what kinds of things you'd be able to prove or
Oh, so that was only an example. I use that network because it's simple enough. And I also happen to have the figure for my class when I was teaching Bray's paradox. So there's absolutely no restriction to Bray's. So it's fully general. So I introduced that routing matrix. So with that, you can address any kind of network you want.
Got it. Larry, I'm still hanging on a bit by a different channel.
Okay, yeah, there is one more question here in the Q&A. Murat, it's from Jeff Shama, your colleague. He asks, are there revision protocols that exploit the additional degree of freedom enabled by delta dissipativity? For example, small gain, quote unquote, revision protocols.
Okay, that's the kind of question that I like. Yeah, so so what we did basically was the following. So we didn't really max out on what we can do with delta dissipativity. So the only thing we did was, let me show you actually this slide. I'll share screen again if I may. Let me go back. So where is it? This one. Okay, so I mean, you're also a robust control guy, Jeff. So you have these separate blocks here, right? So all the evolution dynamics models. So all we did was, if each one of those is actually delta passive, we can weight them with different weighting factors, right? And so then you will get basically, we generated delta dissipativity properties for all of the EDMs by weighting the delta passivity properties differently, okay? So that fails the traditional definition of delta passivity, but gives a weighted form that fit into the generalized dissipativity framework. So small gain and others, yeah, I think that's definitely something to look into.
Great, thank you. I see. Well, here's one more question just came in. Oh, Jeff, he said thanks.
Okay.
So, if anybody has a last minute question, we have maybe a minute or two more.
Yeah, I'm sorry. I think I'm having some. It's not network problems, but some Zoom issue here. So wonderful talk. So thank you. I think